In this module, we explore how molecular collisions lead to chemical reactions in gases and how to determine the corresponding reaction rates. We first extend our discussion to collisions between gas particles of two different types, which we will label as A and B. The relative motion between particles A and B is characterized by the mean relative speed. It is calculated using the reduced mass of the two particles, as we discussed earlier. To understand how often particles A and B collide, we consider a simplified model in which one particle of type A moves through a space filled with stationary particles of type B. In this model, the collision diameter is the sum of the radii of the two particles. The expression for the corresponding collision cross-section is shown here. After traveling for a short time interval delta t, particle A may collide with stationary particles of type B, whose centers lie inside a collision cylinder with volume equal to the collision cross-section times the mean relative speed times delta t. The number of type B particles within the collision cylinder is given by the particle density of B multiplied by the volume of the collision cylinder. We derive the average time between collisions of A with B by setting this number equal to 1. Solving this gives the collision frequency of particle A with particles of type B. The collision density between particles A and B, that is, the total number of collisions per unit volume and unit time, is equal to the particle density of A multiplied by the collision frequency of a single particle A with particles of type B. This results in a final expression. The collision density is equal to the product of the particle density of A and B, the collision cross-section, and the mean relative speed. This simple result reveals two important insights about collisions between different particles. First, unlike in the case of identical particles, there is no factor of 1/2 in the expression for the collision density between dissimilar particles. This is because each collision between particles of different types A and B is counted only once. Particles A are considered as moving and particles B as stationary. Unlike in the case of identical particles, we do not count collisions from both perspectives, so there is no double counting. Second, the formula is symmetric with respect to particles A and B as it should be. If we were to consider a moving particle of type B traveling through stationary particles of type A, we would arrive at exactly the same expression. This property of the formula confirms that it correctly quantifies all collisions between particles A and B, regardless of which type is treated as moving in the derivation. Let us now consider as an example a simple bimolecular reaction in the gas phase, in which species A and B react to form a product P. For this reaction to take place, A and B must collide and a reorganization of chemical bonds must occur. This connection between molecular collisions and reaction rates forms the foundation of the collision theory of reaction dynamics. Not every collision results in a chemical transformation, and the reaction is much slower than the collision density alone would suggest. In fact, most collisions do not lead to a chemical reaction, and only a small fraction of collisions are reactive. The rate of product formation is determined not by the total number of collisions between A and B, but by the number of these reactive collisions. The density of reactive collisions per unit volume and per unit time, which we label ZR, depends on two factors. First, ZAB, the density of collisions between A and B, which we have just determined. Second, the reaction probability, denoted by gamma. It is the probability that a collision actually leads to a reaction and product formation. This probability is typically much smaller than 1. Therefore, according to collision theory, to determine the reaction rate from collisions between molecules, we must determine this reaction probability gamma. To understand why only some collisions between molecules lead to chemical reactions, we must first discuss the energy requirement. When two gas molecules collide, the energy of the collision must be sufficient to drive the rearrangement of chemical bonds. Different types of collisions contribute energy towards the activation of a chemical reaction in a different manner. According to collision theory, it is primarily the relative motion of two colliding molecules along the line connecting their centers, what we call a head-on collision, that is effective in initiating a chemical reaction. Specifically, it is the component of the combined translational kinetic energy associated with this head-on approach that contributes significantly to overcoming the activation barrier. In the simplest variant of collision theory, only the head-on translational motion of each molecule is considered, and it is assumed that all the energy relevant for reaction activation is contained in this motion. To formulate the energy requirement, we further assume that a chemical reaction can occur only if the total kinetic energy of the head-on motion exceeds a certain threshold. This threshold energy corresponds to the activation energy required to initiate the reaction. We denote the activation energy for individual collisions as epsilon A and as EA for the molar equivalent. Obviously, not all collisions provide enough energy to overcome the activation barrier. Without going into the derivation, I will state here that the probability that a pair of colliding molecules has sufficient energy to overcome the activation barrier is described by the Boltzmann factor. Now, Even if the colliding particles possess enough translational kinetic energy, not every collision will result in a chemical reaction. That's because in addition to the energy requirement, the reactants usually need to collide in a specific orientation for a reaction to occur. This limitation is called the steric requirement. To account for this additional constraint, we introduce the steric factor denoted by the Greek letter alpha. The steric factor alpha represents the fraction of collisions that occur with the correct relative orientation to allow the rearrangement of chemical bonds. Typically, alpha is much smaller than 1, especially for reactions involving complex molecules. This is intuitively understandable. The more complicated the molecular structure, the less likely it is that a collision will happen with the precise geometry needed for reaction. We can now express the reaction probability gamma taking into account both the energy and the orientation requirements. This expression tells us that the fraction of collisions which lead to reaction is governed by two factors. First, the steric factor alpha, representing the orientation constraint, and second, the Boltzmann factor, representing the energetic requirement. The density of reactive collisions between particles A and B is therefore given by this expression. It tells us the number of reactive collisions per unit volume and per unit time. The next important point is to recognize that the density of reactive collisions represents the number of reacting particle pairs per unit volume and per unit time. This means that it corresponds to the rate of change in the particle density of the reactants A and B due to their conversion in the chemical reaction. In formal kinetics, however, the reaction rate is expressed in terms of moles per unit volume per unit time instead of the number of individual particles. To convert the reactive collision density into the conventional reaction rate, we divide it by the Avogadro constant. This mathematical transformation shifts the focus from counting individual reactive molecular collisions to measuring amount of substance of reactants converted in the chemical reaction. In doing so, we align the microscopic results obtained within the framework of kinetic theory and collision theory with the macroscopic perspective of formal chemical kinetics. The second part of this alignment is to convert particle densities into molar concentrations. Recall that particle density is related to molar concentration by this relation. Substituting the particle densities with molar concentrations, we convert the microscopic style equation for the density of reactive collisions into a macroscopic style expression for the reaction rate. Thus, starting from the molecular picture of gas phase collisions, we have successfully derived a macroscopic expression for the reaction rate. To present this result in a more conventional way, we rearrange it to explicitly highlight the rate constant K. We can immediately recognize that this combination represents the familiar Arrhenius-like expression for the rate constant. Within this expression, the pre-exponential factor K0, also called the collision frequency factor in this context, can be clearly identified. The obtained rate constant and pre-exponential factor have the dimension of length to the power of 3, that is, volume per time per amount of substance, which is dimensionally consistent with the rate constant of a bimolecular overall second-order reaction. Remember that second-order rate constants are conventionally expressed in a non-coherent SI unit liters per mole per second. Next, let us substitute the expression for the mean relative speed into the pre-exponential factor. It gives this expression. This result shows an important feature. The pre-exponential factor is not constant, but rather exhibits a weak temperature dependence proportional to the square root of temperature. This square root temperature dependence is a distinct feature of collision theory and contrasts with the classical Arrhenius equation, where the pre-exponential factor is treated as temperature independent. Furthermore, compared to the empirical Arrhenius equation, collision theory offers a molecular level perspective that explains the physical origin of both the pre-exponential factor and the activation energy. I will now pose a deeper question. Even though we have successfully derived the reaction rate of a gas phase reaction from collision theory, does this mean we have solved the dynamics of chemical reactions? Not really. Let us recall the parameter we introduced earlier, the steric factor alpha. It was introduced to account for the fact that not every collision, even if it has sufficient energy, leads to a chemical reaction. Theoretically, the steric factor represents the fraction of energetically possible collisions that also occur with the correct relative orientation between the reactive molecules. Given the complexity of real molecular geometries and reaction mechanism, introducing the steric factor seems like a reasonable idea. However, here lies a fundamental limitation of basic collision theory. The steric factor cannot be predicted from within the theory itself. Instead, the steric factor must be determined empirically by comparing theoretical estimates with experimental reaction rates. In this sense, it is not a theoretical result, but rather an empirical fitting parameter. In fact, one might say that the steric factor serves as a measure of the failure of simple collision theory. The way it is used, the steric factor effectively absorbs all contributions of the model's limitations, such as the neglect of internal degrees of freedom, the assumption of hard sphere collisions, the idealization of collisions as binary and central, and the complete lack of quantum mechanical considerations. So, while collision theory provides an elegant and physically intuitive framework to estimate qualitative trends in reaction rates, its quantitative predictive power is limited, especially for complex systems. Despite its limitations, simple collision theory offers an important first step in understanding the molecular foundation of chemical kinetics. From just a few physically intuitive ideas, particles as hot spheres, motion governed by classical mechanics, and reactions requiring sufficient energy and proper orientation, we are able to derive expressions that resemble experimental rate laws and explain key trends in reactivity. Using the concept of molecular collisions, collision theory provides a convincing explanation for the concentration dependence of reaction rates for bimolecular reactions. Increasing the concentration of reactants increases the frequency of collisions and therefore the overall reaction rate. Collision theory also explains the temperature dependence of reaction rates in a reasonable way through the Boltzmann distribution of translational kinetic energy. This helps us to understand why raising the temperature generally increases the reaction rate. More particles have enough energy to overcome the activation barrier. However, we must also recognize what simple collision theory does not capture. It reduces the complexity of molecular interactions to only translational energy and geometry. As a result, it excludes a wide range of important physical phenomena from consideration. Nevertheless, as a first molecular theory of chemical kinetics, the collision theory plays a crucial illustrative role. It provides a clear physical picture of chemical reactivity and lays the groundwork for more refined approaches, such as activated complex theory and molecular dynamics simulations that incorporate additional molecular detail and allow for more accurate modeling of reaction dynamics.